So when we have a wave of charge, there's basically two waves for waves to propagate. As like a wave in the ocean, and we've said this 1,000 times, it's like the P wave, the pressure wave, versus the S, the shear wave, in the way an earthquake propagates in the land. So you got a compressional wave, which is called longitudinal, where the axis of the compressional wave is parallel to the direction of propagation of that wave, called the longitudinal compressional wave, versus the transverse up and down component. Now, every wave has some of both. For example, as we've always said, a tsunami, a tsunami under the ocean is mostly longitudinal. The boat on top doesn't know the wave went under. But when it hits the shore, that vortex curve of the side of the ocean, pushing the vortex upwards, converts part of that longitudinal inertia of the tsunami traveling at the speed of a jet plane. It takes it takes the longitudinal inertia of that compressional tsunami, and because the side of the vortex is the curve of the slope of the shoreline, the compressional wave is converted, a major part of the inertia is converted by bouncing against the side of the vortex of the shoreline into the up and down component shear wave called transverse wave. We're talking about a water wave here, but we're directly implying the metaphor of electromagnetic wave. So that up and down component called transverse, which is traveling perpendicular to the direction of propagation. So the transverse electromagnetics is what all our radio, all our communication, everything is based on, even though our sound waves are based mostly on longitudinal component. The point is that physics does not know how to deal with, to communicate with, to make radio of anything to do with longitudinal electromagnetics.